are off rhythm from each other. So the experiment wouldn't seem to do much, since two rays of light are just traveling the same distance. But in this experiment, the whole apparatus is in motion. We're going to test whether or not motion of the source of light affects the speed of light. The motion that this apparatus is in is the motion of the Earth. It's moving with the motion of the Earth. The direction of one of the mirrors is placed in the direction of the motion of the Earth, the other one being vertical or perpendicular to that. So that if the velocity of light is affected, if its velocity is added or subtracted to the motion of the Earth, it should be out of sync with the other ray of light that travels the same distance but is not affected by the motion of the Earth. I would say thank you to the Lawrence Livermore Laboratories for reconducting this experiment for us, but it was done right here in the office. So the distance BD is equal to the distance BC, and both rays of light are then collected at point E to be analyzed. So let me give an analogy quickly of what this experiment is trying to determine. This might be far out for people to follow, but bear with me. We have a very large treadmill. It's 4 by 4 meters big. This is a treadmill. And the 4 by 4 treadmill is going at a speed of 3 meters per second. Now we're going to have two runners run in directions perpendicular to each other on this treadmill. Both of the runners will be running at equal velocity, or both the runner speeds will be equal. Let me make sure I'm clear on this. So, direction of the treadmill is going in this direction, going in the direction left. If a runner is to, instead of running up the treadmill, runs across it, don't try this at home, and say he reaches the opposite side in 1 second. He didn't simply travel 4 meters. If he would have merely ran straight, he would have fallen off the treadmill. So he has to run at an oblique angle to end up at the target directly in front of him. Which means as he runs up, the treadmill takes him to the left. So he has to run a little bit extra than just 4 meters. So in 1 second, the treadmill takes him 3 meters down. He's trying to run to a target that's 4 meters in front of him. So how many meters does he actually have to run?
5.
Yes, he actually has to run 5 meters to make it to this target. So in 1 second he runs 5 meters. And then how long is it going to take him to turn around and run back to where he started? If it took him 1 second to run across to one side.
Should be the same.
Should be the same, yes. He'll run another 5 meters in 1 second. So if our second runner has the same speed of 5 meters per second, and he runs for 2 seconds, as our first runner did, 1 second, and then a second back, the second runner will run 10 meters in 2 seconds. But meanwhile, as the second runner was running up the treadmill was taking him down each second. So how many meters will the treadmill take him down in 2 seconds? How many meters will the treadmill pull him back?
6.
6. So in 2 seconds, the second runner running at 5 meters per second would have ran 10 meters, except the treadmill took him back 6 meters. So in 2 seconds, he makes it where?
1 meter?
To the end?
You got it, Hector. Yeah, to the end, 4 meters. In 2 seconds, he can run 10 meters, but the treadmill has taken him back 6 meters in 2 seconds. So in 2 seconds, he merely makes it to the end of the treadmill. He hasn't made it back yet. Where the first runner has made it to the end of the treadmill, across the treadmill, and back in 2 seconds. This is the analogy that Michelson experiment was trying to do with light. The treadmill motion being the motion of the Earth. If a ray of light is traveling against the motion of the Earth and then back again, we would expect its velocity to be different than a ray of light that just has to travel the same distance but across. So we would expect them to be out of sync with each other. So let's look again at the Michelson-Morley experiment. So just to make the Michelson-Morley experiment clear, we did a pulse of light. So at the light source, a beam of light is released, it's split into half, 2 equal parts. They travel the same distance, are reflected back, and collected into the interferometer. One of the mirrors are placed in the direction of Earth's motion. The other is vertical to it. So one ray of light is expected to be affected by the velocity of Earth. And with our precise instrument here, the interferometer, precise instrument to the left, we should be able to detect any interference between the two waves of the rays of light. So is our experiment clear? The way we're going to be able to detect whether the motion of a source affects the velocity of light? Because remember what our paradox was. Either the relativity of motion is maintained for light, meaning that the same situation that happens in the laws of mechanics, where they are unaffected whether they're in motion, in uniform motion, or whether they are stationary. Either that situation is also true for the other laws of nature, such as electromagnetism, or the velocity of light changes given the motion of its source.